Good morning, everyone. I welcome you all for this session of radiation. In the previous class, we have taken the heat exchange rate between the by radiation between two black surface elements. Today, we are going to take the heat exchange by radiation between two finite black surfaces. So let us begin with, we have to start with a heat exchange by radiation between two finite black surfaces. So let us consider two surfaces. Let it be of any shape. It's not necessary it has to be on the same shape what I'm drawing. I'm just going to consider two finite surfaces. Let me consider this surface area A1 and this surface as area A2, and let this surface temperature be T1 and this surface temperature be T2. Out of these surfaces, in the previous class what we did was we had taken a small elemental area in this surface and a small elemental area in this surface, where we named this small elemental area as dA1 and this as dA2. The distance between these two surfaces we had taken it as L, and the normal to this surface 2, it is in the N, and the angle between this surface and the normal we have taken it as beta 2, and the normal to this dA2 and the distance of the dA1 to dA2, the angle we have taken it as beta 1. Instead of a small element dA1 and dA2, we have a large element of a surface, of a black surface, and we call it as a finite black surfaces, and I want to know the heat exchange by radiation between two finite black surfaces, for which we already know for a small elemental area. For a small elemental area, the heat exchange by radiation between two finite surfaces, we already know the equation from the previous derivation, that is dq1 to 2 is equal to sigma by pi into cos beta 1 cos beta 2 into T1 raised to 4 minus T2 raised to 4 dA1 into dA2. dA1 into dA2. This is what we had got it from the previous derivation for the small elemental area. Instead of a small elemental area, we have a large finite surface, and that surface area I'm going to take it as A1 and I'm going to take it as A2. In that case, to know the finite element, the whole surface, I'm going to integrate it on both the sides. When I integrate, this will be q1 to 2. This is equal to, I have to integrate over the surface A1 and over the surface A2, because a small elemental area is taken out of a finite surface A1, as well as a small elemental dA2 was taken instead of a surface A2. So dA1 and dA2, to get the whole, for the whole surface, what we do is we just integrate over the surface. So it will be A1 and A2 into, I have the same whatever I have the top, it is sigma by pi cos beta 1 cos beta 2 into T1 raised to 4 minus T2 raised to 4 into dA1 into dA2. dA1 into dA2, wherein which Q1 to 2 will be defined by Q1 to 2. I have Q1 to 2, which will be, I have a sigma which is a constant, as well as T1 raised to 4 minus T2 raised to 4, even that is a constant, because the surface temperature and surface temperature for the surface A1 and surface A2 are same. So it is also a constant. So what we do is, I'm going to take it outside the integration. When I take it outside the integration, it is sigma T1 raised to 4 minus T2 raised to 4 into the bracket. I have, into the integration, I have A1 into A2, integration of A1 A2, it is cos beta 1 cos beta 2 into dA1 into dA2. I think I have missed something here. It is divided by L square, I guess. So this is divided by L square. So this is divided by pi into L square. So within the bracket, I have this part. Within the square bracket, whatever I have. So this can be written as a shape function f1 to 2. It can be written as a shape function f1 to 2, and it is given by 1 by a1. It is given by 1 by a1 and whatever is there within the square bracket into a1 a2 cos beta 1 cos beta 2 into dA1 into dA2 divided by pi into L square into pi into L square. This is what it is there in the square bracket. So to substitute, if I substitute this shape function back in this equation, I'll be having the heat exchange rate between 1 and 2 surface is equal to sigma into T1 raised to 4 minus T2 raised to 4 as it is. Then I have a shape function f1 to 2 into a1. This a1, whatever I have, I'm going to take it here because I'm substituting whatever is there in the square bracket. So I'm taking it to the other side. So it will be f1 to 2 into a1. So the heat exchange, therefore the heat exchange between the two finite surfaces will be equal to sigma into T1 raised to 4 minus T2 raised to 4 f1 to 2 into a1. This is about the shape function for 1 to 2. If I take the shape function for 2 to 1, if I take for the shape function 2 to 1, so f2 to 1 on the similar background, similarly what do I get? Similarly f2 to 1 is equal to 1 upon a2. Instead of a1, I'm going to take it as a2. Within the integration, it is for the surface a1 and a2, and cos beta 1 cos beta 2 divided by pi into L square into dA1 into dA2. So if I substitute, I have Q1 to 2, it is F2 to 1 into A2 into sigma into T1 raised to 4 minus T2 raised to 4 into T1 raised to 4 into T2 raised to 4. This is the heat exchange rate between by radiation between two finite surfaces of which are black. The surface which we have considered is black surface. Moving ahead, let us consider the heat exchange. A heat exchange by radiation between finite surface or finite black surface. Let me take it as finite black surface A2 and a small black surface A1. In that case, I have a finite surface which we are going to consider this as A2, and instead of a larger surface I have a only small black surface which I am going to take it as A1. And when I compare with the finite surface A2, this is very small, and I have a heat exchange rate between these two surfaces, and the distance between these two, again I'm going to take it as L, and this is maintained at temperature T2 and this is maintained at temperature T1. In that case, what will be the heat exchange rate between the surfaces? I know the main small equation, heat exchange between two small elemental area. It is sigma by pi into cos beta 1 cos beta 2 into dA1 dA2 divided by L square into T1 raised to 4 minus T2 raised to 4. In this case, I have A1 is small. A1 is small. That means dA1 which I have taken is equal to A1 only. Because it is small, the elemental area dA1, I have taken a small elemental area, and in this case we have considered a small area of A1, so dA1 will be equal to A1. In that case, my Q1 to 2 will be within the integration only A2, because I have dA1 is equal to A1. I have already taken it. I'm going to integrate it only with the surface A2 into cos beta 1 cos beta 2 into dA2 divided by pi into L square multiplied by sigma into A1 into T1 raised to 4 minus T2 raised to 4. T1 raised to 4 minus T2 raised to 4. In this case, again, if I write down the shape function, whatever is there within the square bracket will be a shape function, that is f1 to 2 into sigma A1 T1 raised to 4 minus T2 raised to 4. That is the heat exchange between 1 to 2. Similarly, on the same background, I'll be having 2 to 1. So this is about the heat exchange between two finite surface element. One is finite and one more small surface. Again, we'll discuss the shape factor in detail. We need to know the shape factor. What is the shape factor? And we need to discuss it within detail. As I said in the previous class, the shape factor of one surface with respect to another surface is a fraction of the radiation leaving the surface which is intercepted by the other. Shape factor is nothing but it is a shape factor of one surface with respect to another surface is a fraction of the radiation is the fraction of radiation leaving the surface, which is intercepted by the other. I repeat, shape factor of one surface with respect to another surface is a fraction of a ray of the radiation leaving the surface which is intercepted by the other. And also we know shape factor will be always within 1, 0 and 1. It will be always within 0 and 1. And also we should know some remarks on the shape factor. The first one is the reciprocal theorem. That is nothing but F122 into A1 is equal to F221 into A2. Say for example, in this equation, I have Q122 is sigma into T1 raised to 4 minus T2 raised to 4 F122 into A1. The sigma into T1 raised to 4 into T2 raised to 4 into is equal to Q122. The heat exchange between the surfaces Q122 and the heat exchange between the surface Q122 is in terms of 1 to 2 will be F221 A2 into sigma T1 raised to 4 minus T2 raised to 4. If I consider this equation as 2 and this equation as 1, this equation as 1 and this equation as 2, and if I equate the right hand side of both the equations, if I equate the right hand side of these two equations, I have sigma T1 raised to 4 minus T2 raised to 4 common. It will be cancelled out. I'm left with F122 into A1, which is equal to F221 into A2. So that is what we call a reciprocal theorem. I should know this reciprocal theorem of F122 into A1 and F221 into A2. And these shape factors, it's not necessary to know the temperature for these shape factors, because when I see the shape factors, whatever from wherever, whatever equations we are seeing it, this shape factor only depends on the shape of the distance between the surfaces and the area of the surfaces. It depends only on the area of the surface as well as the angle with respect to the normal. Only it depends on that. It does not depend on any temperature in this case. So it's not necessary for us to know the temperature to find out the shape factor. So there are many researches done on this to find out the shape factors, and we have already know the values, and these values for different shapes of the surfaces, we are going to take those values from our data handbook. It's not necessary to again sit, calculate those double integration and all, nothing like that. Those double integrations already someone has done it for us. The same values are there in our data handbook. Those values we are going to find out in this problems. Also, I know this equation is very very essential and very very important for me only when either of F122 or F221 is unity. Either of one. that is f1 to 2 or 2 to 1 is unity, I can find out the either of the shape factors directly by knowing the area. So when that shape factor will be unity, where all the from, if say suppose I'm going to consider f1 to 2, what is the shape factor? The shape factor is nothing but it is the fraction of a radiation leaving the surface and intercepted by the other surface. That means when this will be unity, when if say suppose I am going to have f1 to 2 is equal to 1, when this will be equal to 1, when the surface 1 is emitting radiation and all the emitted radiation emitted by surface 1 is intercepted by surface 2, only in that case I can have f1 to 2 is equal to 1. Say for example, I have a convex surface. I have a convex surface like this, and this has been covered up by the another surface. It has been enclosed by another surface 2. This convex surface I call it as 1, and let me consider a small portion of this surface 1 which is maintained at temperature T1, and this is maintained at temperature T2, and I'm going to have a radiation emitted by this surface element 1, where all the rays which is been emitted in the hemispherical direction is being intercepted by this surface 2. I have a surface 2, and all the radiation which is emitted by this surface, that is by this surface 1, is being intercepted by surface 2. So all the radiation emitted by surface 1 is intercepted by surface 2. In that case, my f1 to 2 will be equal to 1. And with this equal to 1, what I can find out, f1 to 2 into a1, this is equal to f2 to 1 into a2. So f2 to 1 is equal to, I can find out a1 by a2 into f1 to 2, and f1 to 2 in this case is equal to 1. So only by knowing the area of the surfaces I can find out the shape factor in this case. I can find out the shape factor in this case. But this is not true for all the hemispherical shapes. It is not true for all the hemispherical shapes. Say suppose I have one surface like this, where I call it as a concave surfaces. I have a concave surface. Again it is enclosed by a surface 2. Again it is enclosed by surface 2, and this is surface 1. It is maintained at temperature T1. This is maintained at temperature T2. If I consider a small element area here which is emitting radiation in all the direction, in this case my f1 to 2 will not be equal to 1, where I have a concave surface, where I have a concave surface. This holds true. This holds true only when all the radiation coming out of it is intercepted by the surface 2. In this case, why it will not happen? Because some part of the radiation which is emitted by this surface is again going back to surface 1 only. Let it be either here or let it be either this side. Here, whatever is emitted in the hemispherical direction, some part of the radiation is going back to surface 1 itself by the concave, because of its concave in nature. Because of its concave in nature, some part of the radiation is going back to the surface 1. So in that case, all the radiation emitted by surface 1 is not intercepted by this surface 2. Some part of it is going back to surface 1. In that case, f1 to 2 will not be equal to 1. So I should be knowing what type of surface it is, and all the radiation coming out from this surface is intercepted by surface 2 or no. Only this can be done by a convex surface or a flat surface or something like that. Also, the second one of this second remarks of this shape function is nothing but value of a shape factor depends only on the geometry and orientation of the surface. As I said in the, it is the second one is the value of it, the value of the shape function, value of the shape factor, value of the shape factor depends depends only on the geometry geometry and orientation of the two surfaces. It does not depend on the temperature or something. So this is my point 2, where value of the shape factor depends only on the geometry and orientation of the two surfaces. The third one is a surface has a shape factor. A surface has a shape factor with respect to itself if it is concave. If it is concave. Say suppose I have a concave surface like this. I have a elemental surface area which is emitting radiation. Some part of the radiation is hitting back to the surface. So I have a concave surface. Some part of the radiation is hitting back to the surface. In that case, my F121 is not equal to 0. So F121, this is only one surface, and 1 to 1 shape factor of 1 to 1 will never be equal to 0 because some part of the radiation is coming back to the surface. In some cases like a flat surface, I have a flat surface. I have a radiation emitting from this surface. In this case, none of the radiation is coming back to the surface. So in that case, F121 will be equal to 0. If I have a convex surface and I have a radiation emitting from a small elemental area on this surface, the radiation emitting from this surface will never be hitting back to the same surface in case of a convex surface. So in that case, F121 will be also equal to 0. Now, instead of considering only one small surfaces, let me consider a room. We are we are having a room. I'm drawing it in 3D. Let's take it in 3D. So I'm going to consider this part, this one as surface 1, surface 2, 3 and 4. This whole as surface 1, this bottom surface as 1, this whole as surface 2, this whole as surface 3 and this as surface 4. In that case, radiation emitted by this surface 1 will never be coming back to surface 1. So in that case, F121 also will be equal to 0 and F222 will also be equal to 0. On similar cases, F333, F323 and F424 will also be equal to 0. But if I consider surface 1 plus surface 2 is equal to A, that is only one surface. If I'm going to consider surface 1 and surface 2 as only one surface, in that case, I'm not going to have FA to A will never be equal to 0, because some part of the radiation is again going back to surface A. This 1 and 2 together, I'm going to consider it as surface A. In that case, there is some part of the radiation going back to surface A only. From A to A, there is a radiation going back to the surface. In that case, it will not be equal to 0. So that I should be knowing. Also, the next part of this, is I have n surfaces making an enclosure. I have n surfaces making an enclosure. Say for example, if I have the fourth one, if n surfaces make up an enclosure, then we have F121 plus F122 plus F123, like that till F1 to n will be equal to 1. On similar background, F221 plus F222 plus F223, so on to F2 to n will be equal to 1. On the same background, if I go down, if Fn21 plus Fn22 on the same background, Fn to n, if I add all the shape factors, the addition of it should be equal to 1. Let the surface elements be anything. Say for example, I have one surface which is flat, then I have one more surface which is convex, then I have one more surface which is concave, then I have one more surface which is convex, then a flat surface. Say I take this as surface 1, 2, 3, 4 and 5. Let it be any type of surface. If it is a enclosure, if it is an enclosure, that means I have 1, 2, 3 to n surfaces. If I have such type of enclosures, let the orientation of the surface be anything. In that case, the shape function from 1 to 1 plus 1 to 2 plus 1 to 3 till f1 to n will be equal to 1. The addition of those shape factors should be equal to 1. This is also very, very important. And the last one, I have a additive relation. The fifth one is the additive relation, where additive relation, say suppose I have a surface, I take it as 1, then I have one more surface here, I take it as surface 2. This surface 2 I divide it into 2, where the top part I take it as 3 and the bottom part I take it as 4. So for me, A2 is nothing but A3 plus A4. A2 is nothing but A3 plus A4. In that case, shape factor 1 to 2 will be equal to F1 to 3 plus F1 to 4. Shape factor 1 to 2, whatever the radiation coming out from the surface 1 intercepted by surface 2, will be equal to the addition of these two shape factors from 1 to 3 and 1 to 4. But it will not make the same if I'm going with F2 to 1 will never be equal to F3 to 1 plus F4 to 1.